everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. In the series of lectures we are doing in engineering physics, today we are going to start with module 3, that is laser and fiber optics. So let us look at the brief outline of this module 3. In part 1, we have laser. Actually, module 3 consists of laser and fiber optics. So we'll consider laser as part 1. And the topics we are going to cover in laser are introduction to laser, stimulated absorption, spontaneous emission and stimulated emission. We are going to understand the phenomena. Then we are going to see some important terms that are involved in laser. That is metastable state, population inversion and lasing action. Later on we are going to see the ruby laser and helium neon laser, and finally we'll discuss the applications of laser in day-to-day life. Now coming to today's topic, we are going to start with introduction to laser. First we'll see the acronym for laser. Laser is an acronym. What is the acronym for laser? We are going to understand. Then we'll see the brief history of laser. Then stimulated absorption, spontaneous emission and stimulated emission. These are the few things that we are going to discuss today. Now coming to laser. A laser device emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. So what we are going to discuss is how light gets amplified. That is what we are going to see mostly throughout the chapter, and how it is done through stimulated emission of electromagnetic radiation. And later on we will see the advantages, disadvantages, or how to apply them. All that we are going to discuss. Now coming to the term laser. The term laser originated as an acronym for light amplification by stimulated emission of radiation. So if you take the term laser, L-A-S-E-R. Here L stands for light, A stands for amplification, S stands for stimulated, and E stands for emission, R stands for radiation. That is how we have the acronym. So we are getting the word laser from these terms. Light amplification by stimulated emission of radiation. This is the first thing you need to understand about laser. Now we'll see the history of laser. Why I want to tell you the history of laser here is, those of you who are interested in research, you will try to understand how the developments take place. When we are trying to find something new, it is not very easy. There may be many obstacles in between. There may be turns and twists. But how do we link one development to the other? And how do we collaborate, or the scientists collaborate with each other and come out with new inventions? That is what you need to understand. So first in the year 1917, Albert Einstein, he lays the foundation for laser technology when he predicts the phenomenon of stimulated emission, which is fundamental to the operation of all lasers. So whenever we talk about laser, it all depends upon stimulated emission. So Albert Einstein, he was the one who predicted this stimulated emission, and this formed the base for laser. Then in the year 1939, Valentin Fabricant, he theorizes the use of stimulated emission to amplify radiation. So whatever theory, the stimulated emission, that was put forward by Albert Einstein, this fabricant, he used it to amplify the radiation. Amplify means to increase. If we are talking about the amplitude, to increase in size. Then in the year 1950, Charles Tornes, Nikolai Basov and Alexander Prokhorov, they developed the quantum theory of stimulated emission and demonstrated the stimulated emission of microwaves. So whatever these two scientists have put forward, Albert Einstein and Valentin Fabricant, they have given a theoretical background. But these scientists, what they could do is, they could demonstrate stimulated emission of microwaves. So what we need to understand here is, unless things are demonstrated, so you cannot accept it. So you will need to, whatever we are theoretically we are expecting, that has to be demonstrated and we should get the result. And once the theoretical as well as the experimental results match, then it becomes a theory. Then later, they received the Nobel Prize in Physics for this groundbreaking work. These three scientists, because whatever was predicted theoretically, they could demonstrate and show the emission of microwaves, and therefore they have received the Nobel Prize in Physics for this groundbreaking work. Then in the year 1959, Columbia University graduate student Jordan Gould, he proposed that stimulated emission can be used to amplify light. So whatever was shown, so stimulated emission, the theory was established, and these three scientists could also demonstrate and show it. So now this scientist, or actually he is a student, he proposed that it can be used to amplify light. Then in the year 1960, Theodore Mayman builds the first working prototype of laser. Here the word prototype is very important. So Theodore Mayman was the first person who made the working prototype of laser at Hughes Laboratories in Malibu, California, using synthetic ruby. So using this ruby crystal, he made the first working prototype of laser. And the first application for the ruby laser was for military range finders. It was used in military, and it is still used commercially for drilling holes in diamonds because of its high peak power. Because it has got high peak power, whatever this scientist Mayman has demonstrated in the year 1960, and it was used initially for military purposes, but even today we are using it for drilling holes in diamond because it has a very high peak power. We are going to discuss about this more in applications. This Theodore Harold Mayman, he was an American engineer and physicist who was widely credited with the invention of laser in the year 1960. And Mayman was granted a patent for his invention, and he received many awards and honors for his work because it was the first prototype of a laser that he made. He received an awards and also a patent. Patent means here he only has the authority to use it and no one can copy it or claim it as their invention. Then his experiences in developing the first laser and subsequent related events are recounted in his book, The Laser Odyssey, and it is republished recently under a new title, The Laser Inventor, Memoirs of Theodore Mayman. And those of you who are interested in research, I suggest that you read this book so that you will understand his experiences. He was sharing his experiences in a very beautiful manner, which helps you to understand how research goes forward. He has shared all his experiences and it is this latest publication. So you can go through this book to understand about it. Now coming to the characteristics of laser light. Laser is highly monochromatic. It has a high degree of coherence, high directionality, and very bright. So all these four characteristics of laser make it very important and also very useful. We are going to discuss about each characteristic in detail. So the first one is monochromaticity. I said laser is highly monochromatic. So what does monochromatic mean? Monochromatic light means light containing a single color. Mono means single. Chromatic is always related to color. So monochromatic light means light containing a single color or wavelength, because we know different colors have different wavelengths, and now we are talking about a single color means a single wavelength. So what we will be mentioning here mostly is it is a light of single wavelength. Then the photons emitted from ordinary light sources have different energies, frequencies, wavelengths or colors. Whenever we are talking about any ordinary light, any source of light which emits light, the photons that are emitted from that source may have different energies, they may have different frequencies, different wavelengths or colors. Hence, the light waves of ordinary light sources have many wavelengths. And it is a mixture of waves of different frequencies or wavelength. That is how we are differentiating between the laser light and ordinary light. When we are talking about laser light, it is a light of only single color. But when we talk about ordinary light, it may have waves of different frequencies or different wavelengths. Then, on the other hand, in laser, all the emitted photons have the same energy, frequency or wavelength. So when we are talking about laser, they have only one color, means one wavelength, so same energy and frequency. So hence the light waves of laser have a single wavelength or color. So therefore, laser light covers a very narrow range of frequencies or wavelengths. They will not have multiple wavelengths or frequencies. They have a single wavelength or a frequency. Now, monochromatic, what we understood here is, laser beam is more or less in single wavelength. We are talking about the gist of it. And the line width of laser beam is extremely narrow. So because it is having a single wavelength or single color, it is extremely narrow, and the wavelength spread of laser light is 1 in 10 power 15. If you are talking about 10 power 15 spread, it is only 1 in that. So narrow it is. So single wavelength, extremely narrow, and the spread is only 1 in 10 power 15. Now coming to coherence. This is the second characteristic we are discussing about laser. Visible light is emitted when excited electrons. Excited electrons means those electrons which are in the higher energy level. They jump into lower energy level, that is the ground state. So whenever we are talking about the emission, if this is the ground state, this is the ground state, and this is the higher energy level, which we also call it as excited state. So visible light is emitted when the excited electrons, the electrons which are in the excited state, they come to lower energy level. That is the ground state. This is the higher energy level, excited state. Ground state is the lower energy level. So when electrons from the excited state jump into the lower energy level, the light is emitted. the process of electrons moving from higher energy level to lower energy level or lower energy level to higher energy level is called electron transition. Because in the next few slides, we are going to talk in terms of transition. What is this electron transition? Electron transition here means either the electrons going from lower higher energy level to higher energy level, means they are getting excited. The transition is taking place from lower to higher, or if the electrons are already in the excited state, if they are coming to the ground level, then they are coming from higher level to lower level. So this is what we call it as electron transition between different levels. Now in ordinary light here we take maybe a lamp, an ordinary lamp or a sodium lamp or torchlight. If you take these ordinary light sources, the electron transition occurs naturally. Electron transition, I told you, the movement of electrons from one energy level to other energy level, that happens naturally. Naturally here means what? The transition, the electron transition is random in time. At any time it may happen. So in other words, what we are talking, electron transition in ordinary light sources is random in time. Random means at any point of time, not fixed. Then the photons that are emitted from ordinary light sources have different energies, different frequencies, different wavelengths or colors. It's because they are emitted at different times and they can occur naturally. So they may have different energies or frequencies, wavelengths or colors. So the light waves of ordinary light sources are having many wavelengths. We have already discussed it. So what we are trying to understand is how the laser light is different from ordinary light with respect to coherence. So the photons that are emitted by ordinary light source are out of phase. So coherence is always related to phase. If they are in phase, if the emitted photons are in phase, then we say they are coherent. But if they are out of phase, then they are not coherent. What is phase here? Phase always talks about the state of vibration. What is phase? Phase talks about the state of vibration. Whenever we are talking about these photons, if the photons that are emitted are having the same phase of vibration, then they are coherent. And if they are not in the same phase, then we say they are incoherent. So ordinary light here, because they are not in the same phase, we say they are not coherent. But laser light is coherent. How we are going to understand? In laser, the electron transition occurs artificially. No? In ordinary light, it is natural. But in laser, it is occurring artificially. In other words, the electron transition occurs in a specific time. So everything happens at a specific time. So all the photons that are emitted in laser have same energy, frequency or wavelength. So that is the main difference between ordinary and laser light, because it is occurring artificially. It is happening at a specific time. The photons that are emitted are having the same energy, frequency and wavelength. Now, the light waves of the laser light have single wavelength or color. So this we have seen in monochromaticity. Now, these wavelengths of laser light are in phase, in space and time. In phase means in the same state of vibration, in space and also at a given time. In laser, we use a technique called stimulated emission to produce light. So we said it is not done naturally. So if not naturally, how it is happening? It is happening artificially with the help of stimulated emission. So the technique we are calling here is stimulated emission, which produces light. Now, what we need to understand about coherence is it is one of the unique properties of light. It arises from stimulated emission, and in stimulated emission, a common stimulus is used. And the emitted photons have a definite phase relationship with each other. So these are the very important terms you need to remember with respect to coherence, unique property. No, it is unique for laser. And also we are using an artificial process which we are calling as the technique is stimulated emission, and we are using a common stimulus, and therefore the emitted photons have a definite phase relation, or they are in phase with each other. Now, when it comes to the high degree of coherence, coherence is the property of the wave being in phase with itself and also with another wave over a period of time and space or distance. So, whenever we are talking about coherence, so it is being in phase with respect to time as well as space or distance. And when it comes to coherence, there are two types of coherence. One is temporal coherence and the other is spatial coherence. And for laser radiation, all emitted photons are in phase. So the resultant radiation obeys spatial as well as temporal coherence. Now, when you try to understand coherence, if you see the waves here, these are, the first diagram represents the incoherent light waves. If you see, we are representing at least 7 waves we are showing here, and the wavelengths of the waves are different. If you see here, one crest and one trough forms a complete wave. So if this is one complete wave, for the second one, here there is one wave. So in this space, we have one complete wave, but here in this space, we have one complete wave. So they are not coherent. Okay. And also if you see the number of waves or the frequency is also different. Here you have in the second one, we have 3 crests and 3 troughs. But whereas in the first one, we have 4 crests and 4 troughs. Means the frequency is also different. So here we are showing the waves which are not coherent. We call them as incoherent light waves. But when it comes to coherent light waves, you see here all the crests are in line. If you see the waves, the crests of each are falling one on the other. And also the troughs are also falling on one the other. So if you see the frequency is also same. The wavelength, if you see the wavelength of the first wave, this is one particular wave and this is the second wave. If you see the wavelength is also same. One complete wave. Now the distance traveled by one complete wave gives us the wavelength. So the wavelength is same. The frequency is also same. Crest falls on the crest, trough falls on the trough. So they are coherent light waves. Now in temporal coherence, which we also call it as longitudinal coherence, the predictable correlation of amplitude and phase at one point on the wave train with respect to another point on the same wave train, then we say it is temporal coherence. For example, you see here P1 is at one point on the wave, P2 is another point on the same wave at a different time. Now, when these two are in phase, then you say it is temporal coherence. It is on the same wave train, but at another point at a different time. Then you say it is at temporal coherence. Then what is spatial coherence or transverse coherence? The predictable correlation of amplitude and phase at one point on the wave train with respect to another point on a second wave. Then the waves are said to be spatially coherent. So here we will talk about one point P1 on this wave And we will talk about another point P2 on this wave, the first wave and the third wave. So we are talking about two different points on two different waves. And now if these two waves are in correlation of amplitude and phase, then we say it is spatially coherent or transverse coherence. Now coming to the third characteristic, that is directionality. Laser beam emits light only in one direction. It travels long distances without divergence. So laser communication is carried out between the earth and the moon. So this is one very important advantage of a laser. It is highly directional. We say unidirectional, means only along one direction without diverging. Without diverging means without spreading out in space. So laser communication is used between the earth and the moon. The directionality of laser beam is expressed in terms of divergence. And how do we measure this directionality is in terms of divergence. The divergence of laser beam is 0.01 milliradian. 0.101 milliradian means I can say 0.01 into 10 power minus 3 radian. Whereas if you're talking about a searchlight itself, we think it is highly focused, or you can focus things using searchlight. It has got 0.5 radian, but whereas laser beam is having 0.01 into 10 power minus 3 radian. This is the divergence. Now, because of the high directionality, the light ray coming from ordinary light source travels in all directions, but laser light travels only in one direction. Now we are talking about the torchlight. If the light that is emitted from a torchlight travels 1 kilometer, it spreads around 1 kilometer wide. When it is traveling through a distance of 1 kilometer, it may spread to a distance of 1 kilometer. But laser light will spread only a few centimeters, even when it is traveling lakhs of kilometer distance. So when we are talking about laser light, when it is traveling even lakhs of kilometers, it will spread only a few centimeters. Here you can see in the diagram, this is the light that is emitted by the torchlight. So the light emitted is spreading. This is what we call as divergence. So when it is traveling through a distance of 1 kilometer, this is traveling through a distance of 1 kilometer, we are scaling up, and it is spreading through a distance of 1 kilometer. But when you take laser light, when the laser light, even if it is traveling through lakhs of kilometers, it will spread only to a few centimeters. So this is what we have to understand about directionality. Now, how do we measure it? The directionality of laser beam is expressed in terms of divergence, denoted by phi. So phi is equal to arc upon radius. Now the arc through which it has spread upon the radius. And how do we measure it is d2 minus d1 upon s2 minus s1. So what are d1 and d2? D2 and D1 are the diameters of the laser spots at distances S2 and S1 from the laser source. Suppose we have a laser source here. Now I take at a distance of S1. So it may be spread through this much diameter. So the diameter of this is denoted by D1. If we are taking the distance more, if we are taking the distance to be more, S2. Now the diameter may be little more, so D2. So if S1 and S2 are the distances from the laser source, D1 and D2 are the diameters of the laser spots. Laser spot means the light that is emitting from the laser. If you catch on a screen, you will have an image of the screen, or we call it as a laser spot. So the diameters if you measure, and also the distances d2 minus d1 by s2 minus s1 gives us the divergence, which we denote by phi. So for laser light, the divergence is 10 power minus 3 radians. So the divergence of light is very low. So we say laser light is highly directional. How we are measuring the directionality is in terms of divergence. If the divergence is very low, means it is highly directional. Now coming to brightness. Intensity of the wave is energy per unit time flowing through a unit normal area. So the brightness always depends upon the energy of the wave per unit time per unit area. In ordinary light, what happens? The light spreads out uniformly in all directions. Okay, if you are taking a lamp, which is a 100-watt lamp, filament, from a distance of 30 centimeters, the power that is entering your eye will be less than 1,000th of a watt. This is to understand the brightness, no, the amount of energy that is spread per unit time per unit area. We are talking about a 100-watt lamp. If you are looking at a 100-watt lamp, then what is the amount of light that is entering your eye is only 1 by 1,000th part of a watt. But in laser, the light spreads in a very small region of space and in a very small wavelength range. So laser light has greater intensity when compared to ordinary light because its spread is less, it has single wavelength, it is concentrated in a small region or space. So what happens? It is having a very high intensity when compared to ordinary light. Now, if you look directly at a laser beam, actually you should not be looking at a laser beam directly because it may harm your eye. But if at all you consider, then what happens? All the power in the laser would enter your eye. Even a 1-watt laser will appear 1,000 times more intense than a 100-watt ordinary lamp. So here we are talking about a 100-watt ordinary lamp, only 1 by 1,000th of it is entering. But here when you look at a 1-watt laser, it will be more intense than a 100-watt ordinary lamp. That is what we need to understand. Now, when it comes to brightness, it is highly bright compared to the conventional light because light is concentrated in a smaller region. And the intensity of a 1 millivolt laser is 10,000 times brighter than the light from the sun. We know we cannot look at sun directly when you look at straight. But if you are talking about a laser light, 1 millivolt, again milli means 10 power minus 3 volt, 0.001 volt laser light is 10,000 times brighter than the light from the sun. Now coming to stimulated absorption. So what we need to understand about stimulated absorption? For that we consider a system having two active energy levels, E1 and E2. We are talking about two energy levels, E1 and E2, where E1 is the ground state and E2 is the excited state. So we see here lower energy state, we call it as ground state. This is ground state. And higher energy state, we also call it as excited state. So what is E1 here? This is E1, which is the ground state. This is E2, which is the excited state. Now, under normal condition, atoms are in the ground state. So whenever we see about an atom, it always generally lies in the ground state. Now, when a photon of energy, h nu, that is E2 minus E1 is supplied, atoms in the ground state absorb that energy and they get excited to E2. Means those atoms which are in the lower energy state, if they have to go to the higher energy state, they need energy. So what we are doing now, we are supplying the energy with the help of a photon. So when this atom gains this energy, and if it is sufficient, here we are mentioning h nu is equal to E2 minus E1, means the difference in energy, at least a minimum of energy which is equal to the difference between the two levels. Suppose this is at 5 electron volt and this is at 10 electron volt. So we need to supply a minimum of 10 minus 5, that is 5 electron volt, for this atom to get excited to the higher energy state. So what we are doing here, those atoms which are in the lower energy state, when we supply energy in the form of a photon, and the energy that is supplied must be at least equal to the difference between the two energy levels, then this atom can move to the higher energy level. So it gets excited to I2. And this phenomenon is known as absorption. Means it is absorbing the light and the light energy, and it is going to higher energy level. And this process is by stimulation. Stimulation means we are supplying the energy externally. We are stimulating this atom to go to the higher energy level. So we also call it as stimulated absorption. Otherwise, we simply call it absorption because there is nothing like spontaneous absorption. Any atom cannot just go on its own because E2 is at a higher level. It requires energy to go to higher energy level. So we need to supply the energy. So we call it as stimulation. So on stimulation, this atom goes to higher energy. So we call it as stimulated absorption. So this is during absorption, how this atom is absorbing the light. But once it absorbs the light, this atom from the lower energy state has come to the higher energy state E2. This is after absorption. So after absorbing the light that we are supplying, the energy that we are supplying, it has gone to the higher energy state. So this is what is stimulated absorption. So now we will see here, if a photon of energy h nu 12, why we are calling h nu 12, I told you, whenever we are talking about a photon, the energy of a photon is given by E is equal to h nu. H is the Planck's constant, whose value is constant, and nu is the frequency. So what is the frequency that has to be supplied so that the energy is sufficient for it to move from lower energy level to higher energy level? That will be the difference between the two levels, 1 and 2. It has to go from 1 to 2. So what is the difference between that E2 minus E1? That has to be provided. So if a photon of this much energy, E2 minus E1, collides with an atom that is present in the ground state of energy E1, then the atom completely absorbs the incident photon and makes transition to the excited state. How it happens, we are going to see. So we have the ground state E1. E1 is the ground state here. This is the E2. E2 is the excited state. Now the atom is in the ground state. If you supply an energy, E is equal to h nu 12, which will be the difference between E2 and E1, E2 minus E1, then what happens after absorbing this photon? What happens here is E1, E2, the atom is now in the excited state. After absorbing this energy, the atom has gone to the excited state E2. So that is what we are calling as stimulated absorption. If a photon of energy h nu 12, this is the photon we are supplying, it collides with an atom in the ground state. So this is colliding with this atom in the ground state. Then this atom completely absorbs this energy and it makes a transition to the ground state. I told you transition is the movement of these atoms from one level to other level. Here it is moving from lower level to higher level. So it makes a transition to excited state. Now, spontaneous emission. What is spontaneous emission? After absorption, the atom is in the excited state. Means once the atom which is in the ground state is absorbing the energy that is supplied, it is moving into the excited state. Now we imagine that the atom is in the excited state. So after the lifetime, the atom de-excites to the ground state. Means this atom which is here in the excited state, it cannot stay there for a longer time. The time for which the atom can stay in an excited state, we call it as lifetime. Lifetime means what? It is the time for which an atom can stay in an excited state. So after the lifetime is over, so it de-excites, means it comes down on its own, thereby emitting a photon. So the energy here is E2, it is at a higher level. This is E1, lower level. Now when this atom comes from E2 to E1, the difference in energy E2 minus E1 is being emitted in the form of a photon. So E photon is equal to h nu, which is E2 minus E1. So this phenomenon is called as spontaneous emission. Why we are calling it as spontaneous emission is, spontaneous means on its own, without supplying any energy. Once the lifetime is over, means the time for which it is meant to be there in the excited state. Once the time is over, it will automatically on its own or spontaneously come down to the ground state or to the lower energy state. And because it is at a higher level, when it is coming to the lower level, it will emit the difference in energy in the form of photon, and that energy is given by E2 minus E1. And this process we are calling it as spontaneous emission. So the photons that are emitted during this emission are out of phase. They are occurring naturally and they have different wavelengths and they are incoherent radiation. So whenever this spontaneous emission occurs, there is emission of light, but whatever light that is emitted is incoherent. It is not in phase because it is occurring naturally and also it is out of phase. Now we will see what is happening here in spontaneous emission. The atom which is initially present in the excited state makes transition voluntarily, means without any stimulation, on its own, without the aid of external stimulus or agency, to the ground state. It emits a photon of energy E2 minus E1. The period of stay of the electron in the excited state is called the lifetime. You need to understand this definition. What is lifetime? The period of stay of the atom in the excited state. The time for which it can stay in the excited state, we are calling it as lifetime. And the process of emission, we are calling it as spontaneous emission. So we'll see the animation, how it is being emitted. Now, where is the atom? The atom is in the excited state, E2. This is the excited state, or we call it as higher energy level. And this is E1, which is the ground state. Okay. Now, for this atom, once the lifetime is over, lifetime means the time for which it can stay in the excited state is over, then what happens? It makes a transition to the ground state. So it is coming from here to here. Then what happens? A photon is emitted, which is equal to the difference in energy. This is E2, this is E1. The difference in energy is being emitted, but it is not coherent. Now, because we are not getting any coherent light there, we go for stimulated emission. So what is stimulated emission here? An atom which is in the excited state is made to de-excite to the ground state before its lifetime. Once the lifetime is over, it is coming down on its own. But when it is coming down on its own, whatever light that is being emitted is not coherent and not a single wavelength, and it is of no use. So what we are doing now here is, before the lifetime is over, we are trying to de-excite it by supplying a stimulus. Okay, what a stimulus we are going to supply with a photon of energy equal to E2 minus E1. So here a photon whose energy is equal to E2 minus E1 is emitted along with the incident photon in the same direction. See, here there is a de-excitation from the higher energy level to the lower energy level, and also we are stimulating it. This is the incident photon. If you see, this is the incident photon, means we are supplying an external stimulus for this atom to de-excite. Now, when it is de-exciting, means when it is coming, when it is making a transition from the higher level to the lower level, what is happening? This is the incident photon, and this is the difference in energy that is being emitted in the form of a photon. So now these two are coherent with each other, a coherent emitted photon. So the photons that are emitted during this emission, they are in phase with each other. They are of the same wavelength, thereby resulting in coherent radiation, which we call it as laser. So in this case, what is happening? Because we are supplying a stimulus, we are calling it is bi-stimulated emission. And because of this stimulated emission, before the lifetime is over, the transition takes place. And when it is coming down, the difference in energy is being emitted as a photon along with the incident photon. And since these two are in the same phase, we are getting coherent radiation, which gives rise to laser. So in spontaneous emission, there is no chance to get a laser because the light emitted is not coherent or not having a single wavelength or not having the same energies. But whereas in case of stimulated emission, what we see here is they are having same phase, so they are coherent. This gives rise to laser. So we'll see the phenomenon, how it is occurring. So the atom is now in the excited state E2. It is in the excited state E2. Now on supplying a stimulus, what is the stimulus we are giving? The difference in energy, E is equal to h nu 12. So for the atom which is in the excited state, we are giving a stimulus, E is equal to h nu 12. This is before the emission. Now what happens after stimulating? What is happening here is this atom which is in the ground state, excited state, is going to come down. And then what is happening? Energy is emitted. This corresponds to the incident photon, and also this is the incident photon and this is the emitted photon. So these two are in phase with each other. Therefore, we get laser. I hope you have understood the very important phenomenon that is taking place in laser, with the help of which you can understand laser. And in the coming lectures, we are going to see more about laser. And if you want any reference, you can refer to books by Palaniswamy, Engineering Physics, and also Gaur and Gupta Physics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.